Hello everyone! Today we're going to start a new unit on solving equations. Now you might think that's what we always do is solve equations, but really we're going to be focusing on special equations. And in our first lesson today, we're going to be focusing on polynomial equations. Now, not every equation is a polynomial equation, but when we solve these, we're going to have to think about how to use the fundamental theorem. Now, I'm kind of wondering, do those words ring a bell from last year? Do you remember polynomials? And what about this thing called the fundamental theorem? Okay, well, you're in the right place. I will tell you that we're going to be covering a lot of material today, but the good news is that it all connects, and there should be pieces of it that look familiar from last year. So, are you ready? Let's take a look at a polynomial. You see, polynomials, they're not just any equation. Polynomials are special. They are typically made up of a lot of terms. As you can see in this polynomial, they're being added and subtracted, and there's exponents. So not every equation is a polynomial. We're not going to be able to have fractions. We're not going to be able to have like a sine or a cosine. The good news is that they're pretty normal looking equations. And when we get these kind of equations, one of the most common things we think about are the roots. Now, roots, which are the same as zeros, which are the same as x-intercepts, you see they all do something. They all make the equation equal 0. It's one of the main things we focus on when we're talking about polynomials. What are the roots? Well, why don't we take a number? Why don't we take like the number x equals 1 and let's decide if it's a root. Now, if we make the word root into a little smiley face, it tends to make people a little happier. But if we take the definition over here, all we're really doing is checking to see if we plug in 1, or I should say when we plug in 1, do we end up getting 0? Okay, because that's what a root is. It's something that's going to make it equal 0. Now, this is actually in essence a pretty easy idea, but kids tend to forget what I'm doing here, so make sure you remember that sometimes all you got to do is just plug it in and find out if it equals 0. Now, I'm pretty sure 1 cubed is 1, and I'm pretty sure 3 times 1 squared is 3. And over here I end up with 4. And of course 4 minus 4 is 0. Well, it's a root. We could say yes. But the reason I really did this was so we could look at the next idea, which is that it says something here about an x-intercept. Yeah, the graph. Now, I'll tell you, for today's lesson, Desmos can come in really handy. In fact, I encourage you to open up another tab, go to desmos.com and fire up that calculator. You're going to want to graph some of these problems with me today. So what will happen when we graph this? What will happen when we type this into Desmos? By the way, when you do type it into Desmos, you can say y equals. You can say y equals x cubed plus 3x squared minus 4. You actually can also keep out the y equals. You can just type in the polynomial. Either way, you're going to get this. Now, did you expect to see an x-intercept at x equals 1? Well, I kind of hope you did. But if you weren't really sure, a root is always an x-intercept. But look, there appears to be another x-intercept, x equals 0. And of course, over here, one more, x equals 4. My gosh, there appears to be 3 roots. Because a root is the same as an x-intercept, all 3 of these numbers should make my polynomial equal 0. Now, getting 3 roots is equally important. That's right, 1, 2, getting 3 roots. And there's something about this polynomial that just says 3. Where do you see the number 3? And which one of those 3's is the important one? Now, it depends on what you remember, but you see this 3 right here? We call it the degree. And you see the degree always tells you how many roots. So this polynomial was destined to have 3 roots because the degree is always equal to the number of roots. We call that the fundamental theorem of algebra. Now, this is a big one, but it's not hard. But anytime you have a degree from a polynomial, it's always going to equal the number of roots. Okay, make sure you get that down. It'll be true today, tomorrow, and forever. And it'll be a nice guide as we work through the problems today. If you think about the problem that we just did, we kind of found a root by plugging in. We also found a root by, well, we found all the roots by graphing. But what if I didn't have those options? What if I just had to find the roots? Well, if you look at this equation without all the extra parts, really what we have is something that can be factored. Now, factoring is also a big deal when it comes to polynomials because a lot of polynomials can be factored. And what I'm showing here is pulling out an x and just figuring out what's left inside the parentheses. It turns out that when I pull out an x, I'm just left with x squared plus 3x minus 4. But that trinomial, well, that trinomial can further be factored, right? If we're kind of thinking about factoring right now, then we want to think about how to break down x squared plus 3x minus 4. And it's just the old trying to find the right numbers that multiply to be -4 and add to be 3. What numbers multiply to be -4 and add to be 3? Yeah, that's right. It's going to be a +4 and a -1. Now, again, I'll say if you weren't ready to factor that, you need to kind of be thinking factoring for the next couple weeks, okay? Because sometimes I need to break down a trinomial so that I can solve each of the factors. Now, when I solve these factors, I'm looking for the zeros. And of course, the zeros that I'm finding are the same ones that we found on the graph. But that's the way it's supposed to work. And so I have my roots. I have my 3 roots. Ready to look at another polynomial? This one's kind of special because, well, it's not really that fancy. It's just x to the 4th minus 81. I wonder how many roots this thing has. It's not hard to know, right? It's going to have 4 roots. Why don't we see if we can find one? I brought along one of my roots. I brought along 3i. Now, 3i is an imaginary number. That's right, 3i is an imaginary number, but we're going to plug it into this polynomial. And I'll say again, if you don't quite remember imaginary numbers, we're going to kind of do a crash course here. But for starters, let's just plug in 3i. Because, well, if I plug it in and it equals 0, then it must be a root. Now, you're probably waiting to see what I do with 3i to the 4th power. So let me help you to take 3i to the 4th power and basically expand it. Let's expand it to be 3i times 3i and then 3i times 3i. Let's kind of pull it apart to be what it is. It's 4 of these 3i's. Now, the reason I put it into 2 little groups is because, well, it turns out that the result of multiplying 3i times 3i is special. When I multiply 3i times 3i, I get 9i squared. Over here, it's the same thing. 3i times 3i, 9i squared. Now, the reason that's special, don't forget about the 81. The reason that's special is because it has an I squared. Now, do you remember? I squared equals -1. That's right, I squared equals -1. So that means I'm really staring at 9 times -1. Of course, another 9 times -1, which is really just -9 times -9. And -9 times -9 is 81. Perfect. I end up with 0. Now, imaginary numbers might need a little bit of some recall. Let me remind you that imaginary numbers come from a strange phenomenon, taking the square root of a negative number. And when you take the square root of -1, well, you really can't do that in the real world. So somebody got the bright idea to say, well, we'll make that equal I. The cool thing, though, is that since I equals square root of $-1, if I square both sides, now I can do that. I can square both sides. I end up with what is really the most important idea, and that is that I squared equals -1. We'll keep talking about that, but trust me, if I have an I squared, that's actually equal to a real number, -1. Well, that was a lot of work to find one root. Remember, we have 4 roots that we have to find. I only found 1. Where are we going to get the other ones from? Before you graph it, why don't we just think about solving it? Like solving it equal to 0. Now, solving this equal to 0 might require a little bit of teacher input, but let me encourage you that we actually can factor this. One of the reasons I can factor it is because x squared and x squared give you x to the 4th. And the other reason I can factor it is because if I carefully choose a -9 and a +9, well, yeah, that multiplies to be -81, and it'll cancel out to be 0. In other words, the term that's missing in the middle. So promise, x squared -9 and x squared +9, those are my magic factors. Now, the reason I factored it is so I could solve it, right? So if I take x squared -9 and solve it, I got myself a little problem I can work out. Like move 9 to the other side and, take the square root of 9. Now remember, as soon as you take the square roots, you get plus or minus. And if I do the square root of 9, I end up with 3. So I'm doing pretty good. I found 2 more roots, +3 and -3. How about this guy over here? Let's set this equal to 0. Let's solve it like a little equation. And, well, subtract 9. Of course, when you subtract 9, you get -9. And take the square root. Uh-oh, I'm taking the square root of a negative number. Okay, no problem. Oops, almost forgot my plus or minus. Okay, get that plus or minus in there. You always get plus or minus when you take the square root of both sides. But yeah, I'm taking the square root of a negative number. Now, the negative, we like to say the negative comes out as an I. But that leaves me with the square root of 9. Well, the square root of 9 is still 3. When it's all said and done, I get plus or minus 3i. Now, in case you got a little confused in there, I just solved that polynomial and we found 4 roots. Well, that's good news because this thing was supposed to have 4. But 2 of them are imaginary, the plus and minus 3i. But 2 of them are real, the plus or minus 3. Let's stop a second and make some conclusions. Okay, first of all, when you have imaginary roots, they're always going to come from an x squared plus. X squared plus 9, but the plus sign is the focus. And whenever you have that, you're always going to end up with a conjugate pair. Now, a conjugate just means a plus or minus, but it's always going to come out to be a pair of numbers. When you have an x squared minus, well, you're going to end up with real roots. In the case of this problem, plus or minus 3. But the focus here is the difference between a plus, which gives you imaginary roots, right? Because you're going to take the square root of a negative number, versus a minus, which is going to give you real roots, right? Because you're going to take the square root of a positive number. Okay, we'll keep talking about that. It's just something to process right now. What about the graph? You were excited to graph it, weren't you? Well, don't get too excited because the graph has a little bit to be desired. Now, I kind of zoomed out on the graph. I changed my window to go the whole way down to -100. Okay, so if you graph it on Desmos, you may not see this exact shape unless you kind of stretch down. But look what we get. We only get, but this is good news, we only get the real roots. We get 3 and -3. I don't want you to think that the imaginary roots are on that graph. They are not. In fact, that's another important conclusion. Imaginary roots do not show up on a graph. Okay, so how do we get the imaginary roots? By solving the equation, but at least I do see the real roots. Hey, by the way, the y-intercept, it's on the graph. It's just something to kind of put in the old brain there when we start talking about graphs a little bit more. Let's do one more problem. And yes, we've done problems different ways. We've plugged in numbers. I don't have a number to plug in here, okay? There's a lot of numbers out there, and at this point, I don't really want to guess. We could factor the problem. Oh, okay. Well, again, factoring, like it or not, it's going to be a big part of this chapter. So we want to kind of brush up on factoring. Now look, when you look at this polynomial, negative x cubed minus 10x squared minus 25x, you should feel like you can factor out let's factor out a negative x. A lot of times we like to factor out the negative just so we don't have so many negative signs on the inside. Of course, that leaves you with 1 less x. So now we're down to x squared. Positive 10, right? Positive 10x plus 25. All right, we got that factored. Kind of feels a little bit like the other problem. Looks like that we're left with a trinomial here. Now that trinomial can further factor. Remember, all you got to do is think about numbers that multiply to be 25 and add to be 10. Okay, we're not trying to make this too tricky right now. It's just going to be an x plus 5 and an x plus 5. All right, so, oh yeah, I did this so that I could solve each of these equal to 0. Now, I'm pretty sure negative 5 makes that equal 0. And I'm pretty sure that negative 5 makes that factor equal 0. Don't be fooled over here. It doesn't matter about that negative sign. It's just x equals 0 makes it equal 0. Now, I should have mentioned, but are you surprised? We got 3 roots. Interestingly, though, 2 of the roots are the same. Yes, when we talk about polynomial equations, we talk about the potential to have the same roots. And in this case, we see the same root showing up twice, but we use a word for that. We use the word multiplicity. Multiplicity, there's 3 I's in there. Multiplicity refers to how many times a root is counted. So we have a multiplicity of 2. By the way, this one also has a multiplicity. It's just kind of boring. It has a multiplicity of 1, because that's how many times that root is counted. There's something special here when we talk about multiplicity. There's something special about the way the polynomial will graph. Once again, I say, do you remember? Let's look at the graph. Now, I don't know what you expected with the negative 5 and the negative 5, but there's no way we're going to cross the x-axis 2 times. We're not going to like cross negative 5 in 2 places because negative 5 only happens at 1 place. But there still is something special happening at negative 5. There's a special behavior. Now, I got a little secret for you. There's a lot of touching that goes on here at the high school, okay? But this is the only kind of touching that we want to see. That's right, when a polynomial touches the x-axis. You see, when a polynomial touches the x-axis, that's a sign to us that there is a special multiplicity. That's a sign to us that we're going to have a multiplicity of 2. Now, it could also have been a multiplicity of 4. It could also have been a multiplicity of 6. But you see, we usually just default to 2 because that's the easiest even number. Technically, we're going to have an even multiplicity. But again, we usually just default to 2. What about over here? What's happening over here? It's not just touching, is it? No, it's crossing. Well, that's more normal. And whenever a polynomial crosses the x-axis, that means it has a multiplicity of 1. Now, it could have also been a multiplicity of 3. It could have been a multiplicity of 5. It could have been any odd multiplicity. But we usually just stick with the number 1 because it's the simplest. These are some important conclusions. Okay, we're talking about multiplicity and the behavior on the x-axis. So again, when you cross the x-axis, which is what happened at 0, you have a multiplicity that's odd. And again, the multiplicity was 1. But when you have a touching, or as I use the word here, tangent means that it just touches the graph and moves on its way. You're going to have a multiplicity that's even. And again, for this one, we had a multiplicity of 2. Okay, so we can look at a graph and we can start to see how many times the root is counted. Okay, and I just want to make sure you're not confused that I'm simply saying that the number -5 is counted twice. And I'm saying that the number 0, x equals 0, is counted once. There's one more thing about the graph. Do you remember? It's called the end behavior. Now, the end behavior isn't just because we're at the end of the lesson. The end behavior is what happens on the graph at the ends. In other words, as you go to infinity. Now, this end over here is to the right. And we would say that the graph is going to positive infinity. You say, but Mr. Eller, it's going down. Yes, I know, but because the graph is going to the right, we say we're going to positive infinity. But yes, it's going down. Now, remember why it's going down? That's because the leading coefficient is negative. Remember, whenever you have a leading coefficient that's negative, it's going to make any graph go down. But the other side, you say, is going up. Well, that's correct also. But that's because it's the opposite end behavior. Now, why is it the opposite end behavior? Well, it has to do with this degree again. And when this degree is odd means opposite. And in this case, opposite means that the right side goes down and the left side goes up. Now, that's a lot to think about, but let's break it down. First of all, the leading coefficient, or as I have it written here, first of all, the degree tells you if the end behavior is going to be opposite or the same. So the degree, remember, the degree is the highest exponent. And if the highest exponent's odd, then we have opposite behavior. But if that highest exponent was even, then we would have seen the behavior the same. But we also have the leading coefficient. Now, the leading coefficient is the first value. And in this case, that first value is definitely negative. And because that first value is negative, we see the graph going down on the right. Now, the leading coefficient only tells you what happens on the right. Okay, the degree is going to tell you what happens on the other side. A lot to process, ideas that you've seen, and ideas that I want you to look at on this very important homework helper. Okay, now, again, it's a very important homework helper. Even though we're not together, I want you to spend some quality time with it. And next time we're together, that's where we'll pick it up.